So when omega s and omega e having same sense of rotation. Okay. So now this is the question that okay, once again. So what I'm saying is that satellite will move in a equatorial plane eventually, even though if you try to orbit some other place, it will not work. And then here I'm trying to explain that because of the different omega, the alignment of the satellite with the point it was facing will keep on shifting, and it will make a periodic alignment, but not always. So this is called the non-geosynchronous. This is just a satellite. I mean, it's not synchronous at all. So the whole idea is, what is the condition for synchronicity? Like when it will synchronize itself. So the simple idea is the given satellite will face the same point on the Earth, or the point below the satellite will be maintained only when the Earth and the satellite will move with same omega in the same sense, right?
Yes.
So for geosynchronous, the condition is obvious. What is condition? So for geosynchronous, what is the condition? The omega of satellite
Is equal to that of the. So geosynchronized means basically like that point P will always be aligning with the motion of the.
correct, always,
Yes.
always.
Okay.
So when point P will be here, satellite must be here.
So that means the speed of, like the angular speed of rotation of the Earth should be same as that of the satellite.
Yeah, so that is the condition. This is the condition. That's simple enough.
Yes.
And then what you need to write is the formula. So we know that omega of a satellite is Gm by r cube, and omega of the Earth is we know is 24 hours, so it is 2 pi by time period, and this will give you something very interesting answer that Gm by r cube is 4 pi square by t square. So there is a very fixed relation that so t square is equals to 4 pi square by Gm into r. And precisely very soon you're going to see that this will be the relation of Kepler's second law. No, this is third law. Yeah. So this is the Kepler's third law, which eventually we'll see. So geosynchronous satellite is a satellite in which, and because everything is constant here, so the distance of geosynchronous satellite is a constant value. So r is not a random value, because for every planet r cube is gm t square, yeah, gm t square upon 4 pi square. So every satellite for every given planet must be moving at a distance of this value to be geosynchronous. And this is not very difficult to calculate. So if you try to do it for Earth, the R becomes so GM. Okay, I'll tell you how to solve questions like this to make it easy. So we know the orbital velocity is how much? GM by R. So GM we can write as RE V naught square. So that's easy to calculate for you. Earth radius, orbital velocity whole square by And to make it simple, because we know the value of v naught, so what I'll do is I'll replace t in terms of v naught. So t is 2 pi, because we roughly take the Earth surface, so 2 pi re. Sorry, just a moment. Yeah, we can write like this: 2 pi re by v naught. No, this is sorry, my bad. This is the Earth time period because that's fixed value. So this is 24 hours. Okay, I should not change this further. Yeah, but you still have to do this much calculation. So R, the distance of the geosynchronous will be 6,400 kilometer, which is meters. 8 kilometer, which is 8,000 meter per second, which is whole square. Time period is 86,400 whole square, and this is roughly 4 into 10, because pi square will take us 10. Roughly we have 10. So you can take all power. So R is 6.4 into 10 per 6.
We
Okay,
can
fine.
cancel out 40 and 6400.
Yeah. I'm writing intentionally that will be power 6, and by 4 into 10. So this is 1 by 2. So 6 power can become 18, and 18 will become 6 again. So R will be 10 power 6. And what we left inside is by 40 cube root. Okay, let me calculate this. I mean, how much? Yeah, so we got roughly 4.8. So this turns out to be R is equals to 4.8 into 10 power 6 meters. So we can attach 4.8 into 10 power 3 kilometers, which is roughly how much? 4,800 kilometers, right?
Yes, sir.
Okay, let me check. I think maybe calculation mistake, but hopefully.
Sir, R is the position of the satellite only, right, sir?
Yeah, R is the. Oh, cool. So the answer is uh, it is 36,000. Oh, I have made some calculation mistake. Uh,
Because it's like lesser than the radius of the Earth.
yeah, that's not possible. So power mistake is there. So mistake. This will be power. This is whole square.
Yes, sir.
This is 64. Actually. Oh, okay, that's fine. It's 8 kilometer per square. So 8 kilometer per second, we can 8,000 per second. So 64 into this way. Yeah. Still, I mean, this is also square. So this is 86.4 whole square. I missed this also here. So now I should get the right answer. Let me just check. Yeah. So yeah, rest is okay. We just missed the square, some squares actually. I'll just make it simple. Yeah, so 8 square and this square I missed. So 6.4 into 64 into 86.4 square. Yeah, and divided by 40, and uh, power is 0.3333. Yeah, so still it's RE we not discuss. You can do the calculation. Something I'm missing. That is my mistake. My mistake. Yes. Yes, we got the answer. This is the right answer. This is the calculation is correct. Only we have made some mistake in calculating. I'm removing the calculation part. So if you solve this, you get the answer. 40 R turns out to be roughly 42,440 kilometers. So if I subtract the Earth radius, so we'll get the height from the surface will be 36,000 kilometer, which is roughly the answer actually. As the Wikipedia says, it's 35,786. So you can see we are getting the close answer. This is the distance of the geosynchronous satellite above the Earth equator. Okay. So why it is important? Okay. So let's say if I have to launch satellite for like taking care of the India's weather.
Sir, are you speaking something?
No, I will not. So, okay. So you got a very close answer, almost correct only. So in gravitation, what we realize that for geosynchronous, that's a simple condition, and that will give you the relation that how far it is possible. So you cannot choose any distance. So in fact, the geosynchronous satellites are fixed in distance. So any country you want to launch, all have to launch to the same orbit. Okay.
Okay, sir.
And that is how they maintain the weather reports and all 24 into 7 because it is always being monitored by the satellites. So we also have the polar satellites. So it is different from the geosynchronous. So the exact purpose is not known to me, but okay, I have never searched. But what I can give you the theory. So we know that Earth is moving around the sun. So in case of polar satellite, let's say this is the Earth actually. Okay, if I do very small, it's not a good idea. So we know that the Earth is moving in a elliptical orbit and all. So a satellite is called polar if it always points above the pole of the Earth. So we know that Earth is slightly inclined to the orbit and makes the rotation. And the polar satellite will be exactly above this pole and will make a motion around the sun along with the Earth. And that's why it will always be above the pole of the Earth, which means the satellite is moving under the influence of sun's gravity, and in a way it has escaped the Earth because Earth is not able to pull it down. So compared to the distance of Earth from the sun, the height of the polar satellite is not too much. So in a way, you make a parallel orbit around the Earth's orbit, slightly shifted up, and that is totally okay for the size of the and the dimension of the sun. And then you remain above the Earth, and that's why it's called the polar satellite. So the time period of the polar satellite will be same as the time period of Earth around the sun. That is 365 days and roughly uh, 6 hours, right? So in 4 years it becomes 366 roughly,
Yes.
because the 6 hours will add up and it will become 4 hours, 624 hours, which will add the one full day, and we call it what do you call?
Sir, 80.
Yeah, it's called leap year. Okay, so there are some many interesting fact about gravitation, that the moon is moving around which planet? Earth, right?
Yes.
And moon roughly takes 27 days and few hours. So you can roughly call 28 days.
Yes.
And this we divide into two fortnight. Sorry, two. This is called yeah, two fortnight. Yeah,
Yes, sir.
and this is equals to 4 weeks. Okay. So basically, the entire motion of moon, if I draw a circle, and if I divide the circle into four equal parts, then every part is like 7 days, 7 days, 7 days. So if I draw the, if I call this as a full moon position, then this is called no moon. So as per the Hindi calendar, we call it Purnima,
Yes, sir.
and we call this as, Hindi calendar Amavas. Yeah, Amavas.
Yes, sir.
Amavas. And as per the Hindi calendar, this is this full moon. So this entire part, the journey from here till here, is called Krishna Paksh. And this is called the Shukla.
So what is Paksha?
The fortnight. Again, you can say it's the measurement of duration. So the entire month will have two paksha. So when you see full moon till you see the some sort of brightness of moon in the sky, you're in the left side, the Krishna Paksha. And when you don't see the moon at all, the darker nights, the nights which are darker, is called the Shukla Paksha, and it happens on a fortnightly basis, and that is how the Hindi calendar is designed. And because we just need 28 days to complete one, or you can say 4 weeks to make it one full cycle of the moon cycle, that's why this is called the lunar calendar. So most of the Asian country, whether it's China or Vietnam or any Asian country,
India.
India also, of course. So what we follow is the lunar calendar. So we celebrate the lunar new year and something like that, with some variation. So let's say we have what you call the Chinese New Year, which they celebrate around the last week of January. Even the Vietnamese New Year is also celebrated around the last week of January. And so the other Asian country, whether it's Singapore or Malaysia or okay, many other countries. So we all follow the lunar calendar, and we like design the days and night based on the moon's rotation around the Earth. So that was the like before the invention of clock, the nature was our clock. So that we learned the concept of time from the repetition, or you can say the periodic behavior of nature. And the great philosopher of old days, they have been able to find this pattern, and that is how the birth of duration or the interval came into existence. The bigger intervals were like a change of season, and then we wanted to have the smaller interval to kind of organize our day-to-day life activities. So that came down to the weeks by the lunar cycle. And then even as the population grew, as the civilization became smarter, they wanted to have the more organized way of doing things. So they discovered the shadow, and they created the hours and later on minutes. And now you can imagine we are so much advanced today that we need a precision of nanosecond interval or even lesser for doing the various research activity.
Yes.
So imagine that from the nature we have come so far to design the clock which can have the accuracy in the picosecond level or range. And that's why we have designed something called the atomic clocks, which takes roughly 10 nanosecond or even less uh, to make a transition, which is called the least interval possible to be measured. So we have gone so far in our life, and the astrophysics, or the you can say the astronomy, is a branch of physics which is not very difficult, but it is necessary to understand how one should launch satellite, how one should follow the trajectory. So a sound knowledge of the orbital, I mean the motion, gravity is essential to become a good astronaut. Apart from knowing physics, you need to know the coding and all. Anyway, so we'll talk about this lunar cycle and how it will help in finding the distance of various other satellites. I mean, sorry, not just distance. In fact, it will also help you in knowing the the time that satellite will take to move around the Earth. Okay, so we can come to this later on. So, okay, so we have seen the satellites. There's one small concept called the energy analysis. So we can just do it quickly. So when it comes to the energy analysis, so you can take any satellite. Okay, no planet is pink, so I will not draw pink planet. Red is called Mars. Yeah, that's fine. Whenever I draw a diagram like this, so what you need to remember, it's an equatorial plane. Okay,
Yes.
so it goes without saying.
So equatorial plane in the sense along the equator of the.
Yeah, yeah, right. So this is the plane. I mean, the Earth is towards you and behind, and what you're seeing is only the plane that the equator will cover. So this
Yes.
blackboard is like the equator, the plane in which equator is lying actually. Anyway,
Yes.
give me 2 minutes. I'm fine.
Okay.
Okay, so if I say the distance of the satellite from the planet center is r, and the mass of the planet, let's call it m, mass of it, let's say. So the the mutual potential energy, because it's an attractive force, so it will be negative g product of mass upon separation, right? Just like electrostatics.
Yes.
The only difference is here the answer will be negative because we have done this in uh,
Attractive force, so work has to be done
yeah,
uh, against to
yeah,
maintain the kinetic energy. Yes.
correct. So now we got the potential, which is very easy, and then comes the kinetic energy. Now every orbit will demand some velocity, so you cannot move just like that. You should have some fixed velocity to be part of this orbit, and we know that this is half m v orbital square, or you can say v orbital is how much? We have done this by the force relation gm by r.
Yes.
So this will again become gmm by 2r. And now comes the energy of the total energy of satellite in a given orbit. And what you can see that it will be the sum of potential and kinetic.
Yes.
So the total energy of satellite, if you look carefully, is exactly half of the potential.
Yes,
Correct? So if you just divide the potential by 2, you get the total energy. That's a very interesting relation. And why this is important? Because we need not to calculate the kinetic at all. So knowing the potential is enough. Also, if you look at the kinetic energy, it is exactly the mod of u by 2,
yes,
which means potential is a really powerful method to get the all types of energy. No need to solve every value separately. And therefore, one should be knowing only potential in solving question. So now the question is, what kind of question we can expect from this discussion? So first of all, we need to plot these energies. So we can see clearly that potential energy is negative, and so the total energy. And what does this mean actually? That a system with a total negative energy is called bound system. So since the total energy is negative, it's called bound system, which means this system will remain in the state perpetually forever. In a way, they are under debt and they cannot be free from each other. So the satellite will be bound to the earth forever till both exist. So to make it unbound or to make it free, if you want to release these two from each other's gravitation, the only method is make the total energy zero. And because the total energy is negative, so you must supply some extra positive energy to make it zero. Understood?
yes,
So now you can see the if the potential energy, if I plot like this, sorry. Okay, this is kinetic energy actually. Because kinetic energy is positive, and the formula of kinetic energy is also how much? G_m by 2 r. So it's inversely proportional to r, right?
yes,
So it is 1 by r graph like this. And now I need to plot two separate graphs, both negative. So which graph represents what? So both negative means one must be potential and other must be total.
yes. Red
So the
is potential and the purple is, yes,
right, because you are adding some kind some positive value to the negative potential to shift upward.
yes,
So any addition will be like shifting upward, and therefore the this color is like okay, you can understand which one is potential.
yes. Sir, so,
Yeah, tell me.
sir, the E less than zero is about, I mean, like the energy is when it's less than zero, it's a bound function. Sorry, bound system.
Yeah,
Like I
like
understand that the object is
right.
stable, but then how is
Yeah,
it like,
Islam is like it is always trapped in the gravitational field, so it may come back to Earth also.
sir,
Like,
how do we make sense of it exactly?
it is like this. So imagine you want to escape the satellite from the attraction power of the Earth. So right now the total energy is negative, which means the system is bound. So they are like trapped in the gravitation of each other. So no matter how you launch, it will eventually either orbit or will bump with the planet. So the motion of the satellite will be governed by the planet Earth if it is not touching it, or if it will touch, then it will bump on come to rest on the Earth. So that is the meaning of bound. It is bound by the gravitation force. When I say unbound, it means their gravitation will not affect each other. So
Yes.
they are the satellite is free from the Earth's gravitation, so it can move freely into the outer space. Understood?
Yes.
Now, to make a system free, you have to make the total energy of system zero. That's it.
Yes.
So let's say there is a question that how much energy we need to destroy the Earth.
So that means like the interaction of any particles with the surrounding should be zero in terms of gravitation.
It means the Earth is composed of particles and no particles should attract each other.
Yes.
The heading looks dangerous. Okay, so you may be banned studying physics if you suddenly come to know, okay, you know how to destroy Earth. Okay. So be careful. Don't reveal this fact to your teachers in school. They may expel you because you're destroying Earth. So maybe you can join the team of Elon Musk. He will be happy.
Yes.
Okay, so the whole idea is if Earth is there, and if the mass of Earth is m, so we know there is something called self energy, and the energy which is required to create the Earth. That's the whole idea from the point
Yes.
masses particles. So we know this answer is minus 3 by 5 GME square by RE. I hope you remember the formula like 3 by 5 KQ square by R.
Yes.
So for solid state it is 0.6 and for hollow it is 0.5, right?
Yes.
Okay. So you can see this energy is negative, which means the Earth is a highly stable system because this much energy has been taken away to create the system. So you must provide the same positive value to destroy the system. So they may ask you that how much explosion is required to. So if let's say if 1 gram of uranium, so if 1 gram of uranium creates few joule of energy. Okay, let me tell you, one atomic mass unit of uranium is able to uh, generate energy roughly 931.5 mega electron volt. So 1 gram means you can understand how much is that. This is exactly, so let's say this is the uranium 235 creates this much. So 235 gram will create how much energy?
This into ME.
Exactly. Can you imagine the energy? Even don't think about it. It's so big now. So 1 gram will create. So to create energy equivalent of this value, so to destroy the energy given plus U self must be equal to 0. So E given will be equal to how much? 3 by 5 And luckily we don't have so much uranium on the earth which we can use to destroy earth itself. That's a good, actually good news, because maybe some psycho can blast the entire earth because you have the energy. Okay.
Yes, sir.
Yeah, people like that also exist, as per the Hollywood movies in which America shows that Russia can destroy the earth. Although nothing is like that, but
Yes, sir. It's politics.
now you know politics also. Correct. So now we can go to the next concept, which is important to us. So we have seen the variety of. See, I am not discussing those uh, things which are very much similar to the electrostatics, which you have already mastered. Okay, but from the satellite point of view, one question which you will come across is called the shift of orbit of a satellite. So let's say they will ask you work required to shift the satellite. So let's say if you have a any planet.
So that we can solve using the work energy theorem, right, sir?
Right. So if we have a satellite which you want to shift, no matter how you want to shift, but if you want to shift it to the launch or something, so shifting means you have to establish from one orbit to another orbit. So every orbit will have its own orbital velocity, so we cannot avoid the velocity. So v will be there forever. But as we discussed, the total energy only depends on the distance, right?
Yes, sir.
So what really matters is the satellite location. So delta E. So what we need to find is the change of total energy, and that will be equal to work done by the agent to shift,
Yes, sir.
and this will be delta U by 2, because we know that total energy is half of the potential, so delta is simple. So what you need to do is find the potential final and before and subtract and divide by 2. That's it. Understood?
Yes, sir.
That's simple question. So yeah, this won't be a difficult thing to think. Okay. So now let me go to the really interesting topic of now. That's called the Kepler's law of planetary motion. So the first law is simple. So up, earlier it was like assumption that the various planets move around the sun in circular orbit, which was earlier assumption. But Johannes Kepler said that no, this is not true, because he observed the various alignment of a star over the years repeatedly, and then from his observation, which he made over his lifetime, he realized that if the path is going to be circular, then the appearance of the star will remain same. Okay,
Yes, sir.
so it was definitely the, maybe you might have seen the brightness of the star. So if sun is kind of, let's say if a star is bright and if you're looking at it, then I think if it is circular path, then you won't be finding it difficult to observe the shift of brightness. maybe it will change because the distance is changing. Also, the other reason we can think is the change of season. If Earth and Sun is equal distant all the time, then it will be heating the Earth in the same fashion always.
Yes, sir.
So we should not have the different or a large variation of temperature of the Earth, which we regularly see during the change of season, right?
Yes.
And for human being, a temperature difference of 10 degree is good enough to be called a change of season. So if the temperature suddenly, let's say, goes from 20 to 10 degree, we can call it in Mumbai, it's cold weather. In
Yes, sir.
Mumbai, even 15 degrees is called cold weather because we are not habitual of such a low temperature. We generally face 25 degrees Celsius. But imagine a person in Chennai, which is a very common temperature. There is like 45 degree to 50 degree also.
Sir, it's not that hot.
I think, but it is around 40 only. Let me check the Chennai temperature. Yeah,
30 to
Chennai is
40
also having the
degrees.
same problem, like humidity problem.
Yes, sir.
Chennai temperature. Oh, yeah, it's 36 to 37 only. That's it.
Yes, sir.
Let's go to Delhi temperature. In Delhi, things are very hot nowadays.
So
Uh,
as an extreme,
extreme goes to more than 50 also.
well,
Yeah, I have with
so are you speaking something?
no, no. So in Rajasthan, if you go to Rajasthan, the temperature is 50 degrees common. Again in Bhopal, Jhansi, it's again 48 degree. In Maharashtra, Nagpur is the hottest, 48. 49 is like Vijayawada is 49 highest. 48, 49 is very common in India. Delhi is again 48.
Yes, sir. So in Oman, it casually crosses 50.
Yeah, but where you stay is more than that. So in Rajasthan, there's a place where Churu, where the temperature is 51 degree, and yeah, Churu is a place where temperature is 51 degree. Right. Okay, in India, 51 is the highest, which is recorded. So after the
Sir, are you able to hear me?
am I audible?
Yes, sir. Now you're audible, sir.
Okay. So before I give you the concept of Kepler's law, I will teach you a bit of properties of ellipse. So before we start, we have to study something called maths. So an ellipse is something like this, a shape like this. Okay, and ellipse can be drawn in two ways.
Sir, Akash sir had completed Ellipse chapter, sir.
Oh, great! So then we can understand this even better.
Yes, sir.
In ellipse, you might have heard about the directrix, okay,
Yes, sir.
and eccentricity.
Yes, sir.
So we'll see a different, the same thing in a different way. So the way I'm going to give you the perspective is quite different than what we have studied. We have to learn in terms of astrophysics. Okay.
Okay.
So what we assume that every planet, let's say the Earth, is moving on the elliptical path, and the Sun is located at one of its foci. All right. So this is the Sun, and Earth is moving around the Sun. So 2 points are of great interest: the nearest point and the farthest point. So this is called R minimum, the nearest to the Sun, and this we call R max. Okay. In astrology, in astronomy, in astronomy, R minimum is called perigee, and the R max is called apogee. So these are of course Greek words, and the Helios is the name of God, right? Helios.
Sir, the sun god.
Yeah, the sun god. So Helios is called the name for the sun, the Greek name for the sun, and that's why the word helium has come from the same word, because the sun will have the excess of helium, and therefore we have the term like a helion. So the nearest point from the sun is called peril, means near, the closer, and helion from means sun. So closest to the sun called perihelion, and the farthest from the sun is called, the far is called apo. So apohelion. So we have perihelion, we have apohelion. Now what is apohelion? It's the farthest. Now what is peri? The nearest. Okay. And see how beautiful these things are. So humankind have been able to observe the minimum separation and the maximum separation, and then comes to the ellipse. So we have something called semi major axis, and the semi major axis is the half of the big axis, right?
Yes.
So this we call semi major axis, and this we call semi minor axis. And we call it B. So you know what is A? A is called the arithmetic mean of the apogee and perigee. So if you add the apogee and if you add the perigee and if you take the arithmetic mean, that's called the A. And that is logical, no?
Yes.
So this is big value, this is small. If you add these two, it will come 2A, isn't it?
Yes.
So that's simple, like the max mean is A. Now what is more interesting, this is the arithmetic mean AM. The B is nothing but the geometric mean of the two. Oh, that's interesting. So that's a very different way of thinking, looking at the A and B.
Yes.
So you might have seen A and B in a one way, but this is a nice way of looking at it. A and B are basically arithmetic and geometric mean of apogee and perigee. Understood?
Yes.
All right. And now comes the semi-lattice rectum. I hope you know. This is called the lattice rectum
Yes.
because the one which passes through the focus and normal to the axis, major axis. And half is called semi-lattice rectum. You can call SLR. And what is even more interesting, that SLR, the inverse of SLR, is basically the harmonic mean of the apogee and perigee. So all the mathematics coming to the same place. And see, it is like the nature is already tuned with these maths. And like, is it some weird coincidence, or God is really kept everything very simple? These things which nature has designed on its own was visible to one person in this universe, and the person is of course known to the world, Ramanuja. So he was able to see everything without any effort. So you can see that nature was talking to him directly. So he conveyed that message to the God. Basically, what he was trying to convey is that he really can connect with nature and extract all the secrets, and perhaps that's how you can call miracle and God. That when nature accepts you, you start talking to nature and you see something which no one can see, and that's how the scientific discoveries are made. So one has to be very much synced with nature. You must love nature. One find that nature will return the favor by giving you some breakthrough in science, and you will win the Nobel Prize. Any. So you can see that everything, only just two variables called apogee and perigee, is giving you all answers, isn't it?
Yes, sir.
So now you must be wondering, sir, but what about the eccentricity? And the answer is yes, I can create the eccentricity also in terms of apogee and perigee, because eccentricity is nothing but the max minus mean upon max plus T. So this is the way in which we look for. This way of looking at the ellipse is only in physics actually. This is not a mathematical way to looking at the things. So there we study in terms of directrix and the ratio of the distance of the point from the focus and the directrix, and we take this ratio as a value less than 1 and we call it eccentricity, right?
Yes, sir.
So did you seen these things before?
Sir, not at this point. I mean, like, not from this point of view, sir.
Yeah, that's why I said okay, I will teach you ellipse, and I was knowing that you will think that okay, this is already taught in mathematics, so why should you taught this?
Yes, sir.
So this is something really interesting for me to see the nature playing with itself, and we are only witnessing this beauty. The how two variables can define everything, apogee and perigee. And if you do the reverse process, if you try to solve this, you'll get all the relation which you want. Okay.
Yes, sir.
So just for the sake of writing, I can just show you one. So basically, the E square is what? R max minus R mean whole square by R max plus R mean whole square, right?
Yes, sir.
So this is you can write as R max minus R mean equals to R max plus R mean whole square minus 4 R max R mean, right? Isn't it?
Yes, sir.
And you can see the equation 1. So 1 will give you that the difference, you can add this, you can replace this by E square into R max plus R mean whole square, right? Is R max plus R mean whole square minus 4 R max R mean. And we know that this is the double of the semi major axis, and this is the square of the geometric mean. So this is how the relation we have. So E square A square is equals to A square minus B square. So B square is how much?
Yes.
And see, I have derived the formula of eccentricity using simple relation. So B is defined as a very different perspective indeed from the maths. In fact, this is so easy that even in maths, if you tend to forget something, then remember this method, you will get to know the answer.
Yes, sir.
All right. So after this basic, we can find the R max and R min also. So okay, we know that R max minus R min is basically E square into 4A square. This is whole square under. So R max minus R min will be how much? 2EA, and R max plus R min is how much? 2A,
Yes,
and we can solve this. So if you add the 2 R max will be how much?
1 plus.
So R max is basically A1 plus B, and R min is basically A1 minus. So if you want to know the eccentricity relation with A, and if you want to write this way, you are free to write.
Yes, sir.
Okay, so after all this formula, we can go back to the Kepler's law. So the first law of Kepler says that every planet moves in a elliptical orbit in which Sun is located at one of its foci. Understood? Okay. And also you should know that this distance is how much? This is A minus R minimum, right?
Yes, sir.
A minus R minimum, which is this much. And you can clearly see this is nothing but AE.
Yes, sir.
So this distance is always AE, and you should remember that from the two foci, if I draw this hypothetically. So from center, the focus is E times away. Understood? It is like the E is like the Snell's law, E times away. Okay.
Yes, sir.
So if I vary the E, what is the purpose of what is the meaning of E here? E means how flat the ellipse is. So if E is 0, it is perfect circle, which means the two focus will coincide with the center itself. So when I say E is 0, it means the two focus right and left will exactly converge at center, and there is no gap. And therefore the ellipse becomes what? Circle.
Yes, sir.
So circle is an ellipse with zero eccentricity, which when the focus or the foci are coincident with the center. So when you grow the E, the center, the foci will set apart on the right and left of the center. So imagine if I make the E infinite, the foci will shift to right and minus, like plus and minus infinity, and in such case we call it pair of straight line.
Yes, sir.
So now you can understand that why infinite eccentricity will transform into pair of straight line, and that is why a pair of straight line can be thought as a special case of ellipse. Understood?
Yes, sir.
So yeah, so that is what we need to understand, that even a line can be ellipse, but not a single line. It must be pair of straight. And when eccentricity is exactly equals to 1, the ellipse will transform into a parabola. So a parabola is something where E is equals to what? 1. Understood? In case of parabola, E is equals to 1. And if E is equals to 1, okay, the minor axis will not exist in such case, and you will get the none of the axis. So you will have just one axis, and the concept of minus and minor and major will go away. And we have like a graph which is open in one side,
Yes,
which
sir.
will never get closed. So one is the critical position where it is neither opening nor closing. The moment you make it less than 1, it will close back and form a closed shape. And the moment you exceed the 1 value, if you go more than 1, it will like opened forever, and we call it hyperbola. So hyperbola is when E exceed 1. Parabola is when E is equals to 1. And anything less than that, we call it. So these are called conics, right? The section of a cone. So we call it conics, a conic section. And in maths, you might have seen that how these conics are created geometrically, right?
Yes, sir.
All right. So after going through this first law, we can just put straight away. So every planet moves around sun in an elliptical and also what is interesting about solar system, that every planet is having their own orbital plane with respect to sun, but the plane of all orbits are not same. So there are two set of planes, or maybe I think three set of planes, in which various orbits are placed, and that is why the orbits around the sun occupies various planes. And because of the shift of plane, their motion is more complex than usual, and two planes come very close, not just because of the periodic motion. The alignment of planet happens very rarely because of the difference of the plane, because one is in this plane, the other is in this plane. So you may have a different radius, but also the plane is different. So the alignment is only possible when you are at the intersection. So when the planets will be part of the intersection, then alignment will take place. That's why there are some alignment which are very rare and which occurs only after a few thousands of years or even more than that. So there are some alignments which a person won't be able to see even in the next future. All right. So every planet move around the sun in an elliptical orbit in which sun is located at one of its foci. Okay. Now, what is the second law? So that is important to us. So this is very interesting, and this says that the line joining the planet or I can say that in a better way, the position vector of planet with respect to sun, the position vector of planet with respect to sun sweeps equal area in equal time interval. That is the aerial velocity. Just I will confirm the spell because I myself get confused with the word ARIEL or EL.
AREALs.
Yeah, that's correct actually.
Yes, sir.
So the aerial velocity of planet remains constant. And basically the second law is a consequence of conservation of angular momentum. So the position vector of the planet with the sun sweeps of what I read. Okay, I'm like too happy. Sweeps. Okay, it sweeps. So maybe I wanted to distribute sweets for no reason. So the position vector of planet with the sun sweeps equal area in equal time interval. That is the aerial velocity of the planet remains constant. Now try to answer this part. If you draw any ellipse and if sun is located, so imagine in time delta t, the planet goes from here to here. So the planet is moving this way. And if I say this is t and this is t plus delta t. So in delta t interval, you have traveled some, or the position vector has swept some area. The shaded region is the area swept. And let's say after some time, you are here. And if I call this as t, then in t plus dt, the planet may travel this much. So if time intervals are equal, then the green area must be equal to, so this is the area swept by the position vector in that time, right? And what we need to remember that this area, if I call this area as A, this must be A. So no matter how far, how closer you are, you will travel exactly, or you will sweep same area in the same interval, no matter what. So let's prove it. And what I said that this is the consequence of conservation of what?
Angular momentum.
Angular momentum. Correct. So it's very easy to prove. So this is the sun, and so you are here, let's say, and you travel a small distance. So I take t and I take t plus dt, and what I have to prove that this area, let's call this as d theta. Okay. So if the planet is here, then first of all we need to know that the angular momentum of the body about the sun will be constant, right? Because the gravitational force will pass to the center, I mean, the sun only. So the torque about the sun will be how much? Zero, right? So torque of gravity about the O will be zero. It means the angular. So when you move in a any orbit, whether it's a circular orbit or elliptical orbit or any random orbit, if the force of attraction is always acting towards the sun, then that torque about the sun will be zero. So angular momentum about the sun will be what? A constant quantity, right? Do you realize this?
Yes, sir.
So from the definition of area vector, we can add dA equals to half r square d theta. So the aerial velocity is called dA by dt is called aerial velocity, and dA by dt will become half r square d theta by dt, correct?
Yes, sir.
And d theta by dt we can also write as omega. All right.
Yes, sir.
So if I multiply with mass and divide by mass, the mr square will behave as the moment of inertia about the axis passing through the center, passing through the sun. So this is like I O omega. Understood?
Yes, sir.
And angular momentum about O is itself at that instant IU, where I is the moment of inertia about the axis which is normal to the plane, like perpendicular axis. Understood?
Yes, sir.
So first of all, you need to realize that the sun is the point about which we are conserving the angular momentum.
Yes, sir.
So I omega we can write as LO. So since L naught is constant, implies that dA by dt is also. Is this clear?
Yes, sir.
Any doubt in this?
No, sir.
No. Correct. So dA by dt turns out to be L naught by 2m, and therefore, so we can also add dt equals to how much? So the time period to complete the full revolution around the sun will be equals to the total area swept by the position vector in one time period, and this is the area of the ellipse, right?
Yes.
So this also gives the third law from Kepler, that is the total time period around any planet is equals to 2m by L naught into area. That's a simple relation. Understood? And we know that area of the ellipse is how much?
Yes.
Pi minor into major axis. Okay,
Yes.
all right. So knowing this answer, we can go to the third law. And third law says that the square of time period is proportional to u of semi-major axis. And third law is also true for the circle, because circle is a one special case of ellipse in which the minor and the major axis both are equal to the radius. Understood?
Yes.
So don't think that we are deriving for ellipse, so it is true for ellipse. You can also freely apply for the circle. That's very easy. So what we can write and how we can prove it. So we know the time period already. The formula time period is how much? 2m by L naught into pi AB, right?
Yes.
And we are trying to write the answer in terms of A. We are not interested in terms of writing B. And therefore, the biggest challenge is what is the L naught? Because L naught I have written as a symbol, but what's the actual value? And the answer we must derive in terms of the known quantities like mass of sun, because the governing mass is sun here, and the earth or the planets will act as a satellite, right?
Yes.
So we don't take a general case. We to find L naught, we pick the because if you to choose this point to find the angular momentum, then the variables which you need to know is V, R, and the angle alpha, the Rn. And alpha is unknown, V is unknown, R is unknown. So that's why we don't choose. So if someone will ask, can you express the R in terms of A? The answer is no, it's even a difficult job. Okay. So what possibly we can do? Okay. What possibly we can do? So there are many ways, but we wait for the planet to reach these two destinations, the apogee and perigee. Why? Because
That would be fine.
at this point, the alpha becomes 90 degrees. So if you draw the R vector, then these R vectors and these V vectors are mutually. So if I call this as R max, R mean, so at the maximum distance, the velocity becomes minimum actually, and at minimum it becomes maximum. So the angular momentum we can write as about O as orbital only, mvr. So we are going to treat the planet as point because the spin will not matter. The spin remains constant, although we can write, but we are assuming it's constant. So if spin will also change, then it becomes really challenging to us. So angular momentum we write as mvr. So we can write as m v mean r max, and if you write at the perigee, it will become m v max r min, and you can see m cancels out. So the product relation is very famous that the V min R max is V max R min, which is very interesting relation because the V max upon V min is same as R max upon R min. And why this relation is important in astronomy or physics? Because the eccentricity we can write as R max minus R min upon R min max plus R min. The eccentricity you can also write in terms of velocity. So we were not aware of the distance of apogee and perigee, and okay. So from geometry, you can replace even if you know the velocity relation. So eccentricity can be written in two ways. You can use the component or dividend to prove. But I hope you can understand this why this both are true.
Yes.
So one should be aware of that eccentricity can be written in these two ways. Just okay. This is not required, but we really need this question. Okay. And what you can see that the R max and R min is known to us because V max. So if you want to express in terms of eccentricity, the R max was 1 plus E, if you remember. So the ratio only depends on eccentricity. So eccentricity is such a famous thing in elliptical orbit case. So V max upon V min is actually this ratio 1 plus E. 1 plus E. You can again use the component and dividend. So once you know the once you conserve the angular momentum, you get the relationship between these four variables. And out of four variables, we know the two variables are known to us in terms of semi-major axis because we are trying to express in terms of A. So R max and R mean are known to us already, and therefore the number of variables is reduced to only two, which is V max and V mean. Is this clear?
Yes.
So if somehow we can find Vmax and Vmin, we can go back to the first equation of L naught to get the L naught, right? So we need one more equation, and the other equation will come from the conservation of mechanical energy. So that's how we solve every question of elliptical orbit. There are just two things to be conserved. One is the angular momentum, and other is the energy. Okay. So from conservation of mechanical energy, so the potential plus kinetic, or you can say like this. So U plus K at perihelion must be U plus K at apohelion, right?
Yes.
So now you can understand that why the word Apollo came. Apollo is again from apo, the far, and it's again sun only. So Apollo is again called sun only. The
Yes, sir.
Helios is the god name. I mean, like there are many ways, Apollo and all. So you can see that how the literature is using the culture actually, and that also shows that a lot of work has been done in astronomy by the Greeks and the Indians both. So we do have a lot of nomenclature in astronomy, and if you look at the astronomy, you can see variety of Sanskrit words. But if you look at the other part of physics, you won't see much of the influence from the Indian culture. The
Yes,
Greeks were much ahead in terms of development of astronomy and science as well. So they have influence all over the world, especially the Europeans. Americans are good with computers. So most of the American research is all about the use of knowledge for the applied science. So Americans use the knowledge from the world. So they brought the best mind from the world. They hired the best scientists, Nobel laureates, and they designed the application world. And so the first, you can say, the Silicon Valley was made in America. So you can understand why and how they are really good businessmen actually. So Americans are basically businessmen. They don't try to develop the core science that is they have left to the world. And once you develop it, they will hire you at any cost. The cost is not a matter for them. They'll give you the best of the facilities and all. Okay. So you can get your value for sure. If you have something, America will respect you. Anyway, coming back. So if I write the U and K at very here and upper, it's very easy to write the answer. So what you can write? Potential is very simple. Minus G, mass of sun, mass of planet upon perihelion is R minimum, right?
yes,
And the kinetic will be half M V maximum. So I will just write as just to make it simple V1 and V2. Yeah. What I'll do is I'll do this now. So now this is R1, okay, plus so what you can also realize that what matter is only the mass of the governing planet, which is Sun. Sun is controlling everyone, so your mass will not matter. The orbit belongs to Sun. It is something like like the it's my locality, and what matter is what I will decide. You have to just follow it. So every orbit, when I say the Sun's orbit, it means to move in that particular orbit, you should have some value, and the mass of the orbiting planet really doesn't matter. It is something like a road in which you have to pay a certain tax to walk around. So orbit is something very, you can say, a holy thing for every planet and the stars. And when I say this is the orbit of Sun, it means to move in that orbit, you must have something. Okay, and what something is here? Anyway, orbit belongs to what? The governing uh, planet. So Sun is governing all planets. So Sun is the Swami of the solar system, right?
yes, sir.
And the rest are the slaves. So it's like the king and the slave. Yeah,
Yes, sir.
like, yeah. So now we have the formula minus G sun upon R1 plus sorry. So you can rearrange the terms. V1 square minus V2 square is twice of GMS of, and we know the ratio of V1 and V2 in terms of R1 R2. So V1 R1 is V2 R2. We know, correct? So you can find V1 or V2 or like whatever you want. So let's say find V1 and V2 kinetics. All right. So what do you get here? Now you can simplify this because R2 and R1 cancel, so R2 plus R1. Hmm. All right. All right. So we got the V1 and we want the answer in terms of A. So we know R2 is how much? What is R2? R2 is A1 plus C, and R1 is A1 minus C. And R1 R2 is I think 2, right?
Yes.
Uh, so V1 turns out to how much? Yeah, simple. And if it is a circle, then E becomes 0. So we get the just GMS by A, which is the known answer. And for V2, no need to solve. Just reverse the sign in the terms. Okay, so a big answer. It looks difficult. Maybe many will stop learning this chapter because of the formula. But it is very easy to see that every derivation we can do in one particular fashion. Okay. And therefore, okay, we got V2 and now time for the angular momentum. So LO, because I don't need much value. So what is L? M V1 R1, or you can say M V2 R2, but I just need one. So the time period we got is how much? What is time? 2m by L naught, no? Into pi a, right?
Yes.
So you can just substitute first. So 2m by L naught is how much? M V1 R1. And V1 we got how much? Oh no, it's a big value. So V1 you can write as okay, that's right. V1 is, so V1 is how much? 1 plus And R1 is how much? Okay. So it's R1 square. Yeah, because we have squared.
Yes.
And no, it's here. So what we have? So it is A square. Okay, like this. And now what you can do, you can substitute B actually. Uh, and B square is A square. So I hope you can see something.
Sir, all the E gets cancelled.
All E term gets cancelled. So we can see clearly that T square comes out to be how much? 4 pi square upon GMS into AQ. And because this is the constant, so this is the formula for time period for every planet moving around the sun. So M represents the governing, the Swami. So for the satellite which is orbiting Earth, the M will be replaced by Earth mass, right? That's why Kepler said that okay, T square is always something, and this relation has nothing to do with the planet. So you can apply for a moon Earth system, you can apply for sun Earth system, or you can apply for some black hole and well, I mean the solar system. Anyway, so do we really need to prove this lengthy? The answer is no, of course not. This is not required. But this you can prove for a circular path which is very easy. So when you try to prove for circular orbit, you get the same relation without much effort. So that's pretty easy. And now, once we know why we this is so, I mean, beneficial, because so if you remember, we solved the question of geostationary satellite, right?
Yes, sir.
I mean, let's see how to solve the question of finding distance of geostationary satellites. And using Kepler's law. So the distance between the moon and the earth is roughly 3,84,000 kilometers. That's a nice information. And time period of moon we know is 27 days. We keep 27. Why? Because the cube root is easy to find, right?
Yes, sir.
So for geostationary, now try to understand this concept. Yeah. For geostationary, the time period is exactly 1 day, 24 hours, right? Do you realize this?
Yes, sir.
So T moon whole square by T geo whole square must equals to distance of moon square by distance of satellite whole square. Sorry, cube.
Yes, sir.
So the distance of satellite will be and see how interesting it is. The satellite is 1 day. This is 27 power 2 by 3, which is like
By 9.
1 by 9, right?
Yes, sir.
So geostationary satellite is exactly 1/9 the distance of moon. Simple answer. Let's see how much this gives. 3,84,000 divided by 9. Ah, cool. It gives 42,666 kilometers. Okay. And if you subtract the Earth radius, it will give you roughly 36 to 66. The height of satellite. So this answer is very uh, confirming that Kepler's law is quite true, right? So I have shown you the answer using the basic derivation.
Yes,
And now the Kepler's law is coming at our rescue. And the benefit is that knowing the answer of one satellite around the given planet, every other satellite must have this recurrence, this relationship, and which will help you in actually using less formula to get the answer. I mean, less calculation to get the answer. So we use the motion of natural satellite to understand the motion of other man-made satellites. So that is how we understand the various thing about gravitation. So the rest, like I have solved variety of questions in the notebook. You can solve, and some question I'll give you separately, which we can discuss. Okay, no need to worry because I will again discuss the conservation of angular momentum type of question in uh, no, we have discussed already. So I think I have discussed something like aiming parameter, right? If you remember,
sir. The aim parameters.
in angular momentum, like the distance of minimum and the closest approach when you throw away from the.
Yes, sir.
So in case of nucleus, if you throw something a positive charge here, it will just go like this. In
Yes, sir.
gravity, we have a planetary. If this is a planetary, if you throw some object, it will go this way. So this is the
Yes, sir.
minimum, and this is called the aiming parameter B. So this kind of question will come in gravitation anyway. All right, so I'll cover the rest of things later on. Okay. So you finished from the notes, and if you have doubts, we'll discuss the doubts and questions also. You can start solving the numericals from. You can start with the SC Verma. I'll share the some PDF. You can practice from there, and we'll come back to the rest of the concept of capacitor and electrostatics and so. Electricity and so on. So next chapter, what do you want to start? The 11th or 12th?
the 12th standard one, sir.
Yeah.
I guess we have to now start with capacitors.
Yeah, right. So we'll go back to 12. And in between, we can come back and solve a small chapter of 11th and we'll go back there. That's a good one. So we can take a break like this. All right. Good night. Take care.
Good night, sir. Thank you, sir.
Next
Bye,
day.
sir.
Good night.
Yes, sir.
It's the next day here in India.
Oh, yes, sir.
Morning 12:50.
Yes, sir.
Bye.